As we set out to deploy neural code completion to Visual Studio, we realized that we can significantly improve the efficiency and accuracy of existing methods. In our MSR paper, we discussed these improvements, which are now deployed to thousands of users. A code completion system needs first and foremost to offer accurate suggestions, but it should also have other properties. It should be fast, as we cannot expect our users to have access to high-end hardware. It should be quite small, ideally only a few megabytes, so that it doesn't bloat the developer environment. And of course, it shouldn't send your code to anyone. To find a good trade-off, we perform a multi-target evaluation of a variety of models. By spending more than one GPU year of compute, we calculate Pareto fronts like the one shown here among accuracy, speed, and size. First, we create a conceptual framework for machine learning code completion. It exposes the main design decisions involved here. Given some partial code context, we use a candidate provider to get all potential completions within the current context. We also encode the partial context with a neural network. Finally, a completion ranker accepts the encoded context and ranks the candidate completions which are shown to the user. By testing a variety of concrete neural components and configurations within this framework, we compute our Pareto plots. The first decision is how to represent our code tokens. Token-level encodings treat each token as a unit. We find that although this encoding is fast, it requires a lot of memory and doesn't generalize well to previously unseen tokens. Subtoken and byte-pair encoding-based encodings split each token into parts. We find that these encodings require much less memory, can generalize to previously unseen tokens, but come at a small additional computational cost. This confirms prior work. Finally, character-based encodings are very memory efficient, but are computationally costly and don't seem to have representational capacity. However, the most important design decision is how to retrieve the candidate completions within a given code context. Traditional neural models have a vocabulary of known tokens or subtokens from which completion candidates are computed. We find that such methods are relatively memory inefficient and their accuracy is average, since the vocabulary tends to be large. However, even before machine learning, there were static analyses that effectively narrowed down the set of valid candidates. In places where such analyses work, our neural methods can instead rank the candidates returned by the static analysis. We find by doing this, we can significantly improve both accuracy and memory efficiency. So, we start with the standard static analysis methods that have been around since the 90s. Static analysis yields an alphabetically sorted list of valid candidates. In the Bastigate, research looked into language models that neurally encode the code context and without additional information try to predict the next token. Instead, in this work we find that if we let a neural model rank the relatively small set of valid candidates of a static analysis, it gives great improvements. By further using subtoken encodings, we can reduce memory usage and improve generalization. A compressed version of this ranking model with just 50 megabytes of parameters has been deployed in Visual Studio. It sees hundreds of thousands of code completions per workday and serves each suggestion within 20 milliseconds, achieving an accuracy of 70% within the top 5 suggestions. For more information, please look at our paper.